Hi there. Today we're going to finally get into some ideas from calculus. In our pre-calculus class, we learned a lot about the stuff that we need to know prior to calculus, but in this last chapter on limits and derivatives, it's kind of a taste of what you're going to actually see in calculus. We're going to start off and look at limits so that we have a full understanding of limits, and this is day one of that. Now, there's two fundamental concepts in calculus, or two problems that they work with, and they talk about the tangent line problem, and we're going to get into that pretty thoroughly. And then there's the area problem we probably won't get into, but that all of calculus kind of revolves around those two concepts. Now, a limit is an important part of those problems. A limit is a quantity that can be approached, and that's important. That's an important word right there. It can be approached. Sometimes that quantity actually is reached, and sometimes it's not. We're going to look at both types, but you have to understand that the limit is always about what the function is approaching. One of the first ways that we would look at that to see what the limit is approaching is to look at a table. Let's look at this example. Use a table to estimate the limit. This is the notation. This will be a new notation for us. It's the limit as x approaches 2. You maybe have seen this sort of notation where it is like as x approaches, in this case 2, y approaches, and then we would have to find out what y approaches. This is kind of a pre-calculus sort of notation, but it's also really representing a limit. As x approaches 2, what is the limit, or what is y approaching? Looking at this example, I'm going to let x approach 2 in this function and see as it approaches 2, as x, you can see in my table, as x gets closer and closer towards 2, and I'm going to approach it from both sides of that, what is the value of the function? What does it look like that my y value is approaching? There are different ways to do this efficiently. You know, you can sit there and type each one of these individually in your calculator. I'm not sure that's, I don't know. You can use a table. You can do second calc and do the value. That's probably faster than the table itself. Some of you and I'm going to try it like this today. I'm going to type in 3, and then in parentheses, I'm going to put 1.9. And I'm going to go ahead for where I'm headed, where I can see the values that I'm going to be plugging in. I'm going to go ahead and put 0, 0 after that. Oh, I'm going to add another 0. No, there we go. 1.900, and I'm going to put that in parentheses. 3, and then parentheses, 1.900, close the parentheses, minus 2. And that's going to be the function that I keep using. So when I hit that, when I type that in, I get a value of 3.7. I'm just filling in my table at this point. I'm going to put in 3.7. Now, because of the way I entered in my calculator, I can very quickly then just bring that back, and different calculators bring it back differently. I did second entry, and it brings it right back, and I can change that to 1.990 and press enter, and I get 3.97. Okay, and then I'm going to try one more time. I'm going to do second entry and change that to a 1.999, and I get 3.997. Now, remember, you're trying to look to see what the limit is, or what the y value is approaching, and as you can look at your numbers, it sure looks like it's approaching 4, and I would guess that that would be the case. But sometimes the functions are weird, and they might approach one value from the left and a different value from the right. That will happen to us for sure. We want to make sure that it's approaching the same value from both directions. We do the same thing then on this side. We look and see what is happening with this. So I'm going to go back and do second entry, and this time I'm going to put in 2.1, and just to hold those places for future, I'm going to put a 0, 0. I get 4.3. second entry, go try a little bit closer. This one is 0.01. And I have the 0 still there. I got 4.03. And one more, just to be sure, I type it in, 2.001. And I get 4.003. And it certainly does appear like it's getting closer and closer to 4 from this direction. Based on this table then, I would say that as x approaches 2, the function has a limit of 4. We write that with a capital L. Limit is equal to 4. Now, that's looking at a table. Let's try looking at a graph. It's the same function. Notice it's just a linear function. It's a pretty basic one here that I'm starting with. You can see that it's been graphed with a y-intercept of -2, has a slope of 3. And I'm going to look at what's going on graphically as x approaches 2. What that means is I've got to, right here is x value of 2. And my function has an x value of 2 at this spot right here. That's the spot that I'm kind of approaching right here. So as we come in from the left side along that function, and as we come in from the right side along that function, and I am approaching this spot where x is equal to 2, and I'm getting closer and closer, what does it appear that the y value is getting closer and closer to 2, or closer and closer? It looks like my y value is getting higher and higher and higher. This side it's getting lower and lower and lower, and it looks like it ends up approaching this y value of 4. Yep, I should be getting the same thing whether I do a table or a graph. And then another thing that we could try is we could look at this algebraically. The title of your textbook, whether or not you ever notice it, but it's Pre-Calculus, Algebraic, Numeric, and Graphical. And so that's kind of what we're looking at. We're looking at algebraically, we're looking at it numerically through a table, we're also looking at it graphically. Or all three of those, sorry. Okay, so let's look at it. And again, this works great because it's a nice, simple little function. You can actually look at it algebraically and just use substitution. Could we just take this x value that's approaching 2 and put it in right here? What's 3 times 2? Minus 2. Well, heck, you just get 4. Wouldn't that have been way easier to begin with? Okay, that's the algebraic way of finding the limit. That gives us 3 different ways, 3 options to finding a limit. And that's kind of our goal today, is we're just going to practice all 3 of those because they each have their own place where they would be the best method. On that previous example with that simple little function, algebraic was by far the quickest, easiest way to look at that one. But you don't always know what's going to happen. We have to know all 3 ways. Here is why that worked so nicely. If you have a continuous graph or a continuous function, and remember a continuous function is one that just kind of flows nicely. There's no gaps, there's no holes, there's no asymptotes, there's nothing. It just flows beautifully. Like something that does this, you know, like a polynomial function. It just flows along without any breaks in it. Substituting is going to be your best bet. But if it is not continuous, that's what we're going to have to use the other methods for. The definition then of a limit, what we have found is the limit is the value that your y value approaches. And remember this key phrase, it is what it's approaching as your x approaches some value c. I have this set up right here. X is approaching c. This is the way that we always write it. The limit, and this is how it's read, the limit as x approaches c of the function, whatever that is, and I have f of x here, but we'll write what the function is in there, is equal to L. And L is your limit then. Now the existence or non-existence of f of x when x actually equals c has no bearing on the limit. For instance, that c, when I did that direct substitution right into the function, that worked beautifully. So the the existence of f of x was good. It was there. The non-existence would be like when you got some sort of an issue plugging c in, if it became undefined or something. That really has no bearing on it because we are always looking at what it is approaching. I don't really care what it equals at that spot. Sometimes it conveniently equals my limit, but it's really, that's just a coincidence. I'm looking at what it approaches. Let's try one that you see what I'm saying where it's not quite so straightforward. Finding a limit when direct substitution won't work. If you look at this one, I have x approaching 1. Big ol' messy function. And I could do direct substitution and start plugging 1 in for all the x's, but look right here. What's going to happen in my denominator if I plug in a 1? That is not going to work. I can't do direct substitution. That's why we have the other methods. Let's go ahead then and go to our calculator. And so this one's definitely messier than our previous one. And I think this is going to be kind of ugly to try to do like we previously did. Look at how many times I would have to be typing in these numbers. These are going to get typed in right here at the x cubed spot. It's going to get typed in at the x squared, at the x minus 1. I'm going to type that crazy number in many times. Let's try something different. Let's do a value. I'm going to go to y equals. And I'm going to type in this function that I'm trying to take the limit of in my y equals. Open a parenthesis for the numerator and do x to the third. If you don't have your calculator, you want to be doing this with me. So pause the video and get your calculator if you need to. Minus x squared plus x minus 1, and then close the numerator, divided by, open a parenthesis for the denominator, x minus 1, close the denominator. And then what I'm going to do is I'm going to go do value, where I can just type in numbers. And you might find that this is your favorite way to do it. It's maybe faster. You're going to hit second trace, which is your calc button, and you're going to do value. And what's nice about value is that you can just type in a number. It says x equals, I'm going to put 0.9. And then you can see that when you do that, it comes back with a 1.81. And you can start filling in your table then with that information. And you don't even have to do anything, I just type in my next number, 0.99. It automatically goes to that value again. And this time I have 1.98 plus a few decimal places. And then I'm going to just type 0.999. So this moves pretty quickly if you like this method. And what does it look like that as my x is getting closer and closer to 1, because that's what x is approaching here, what does it look like? Sorry, I was fixing my little pointer here. What does it look like your x is getting closer, or your y value, or your function is getting closer and closer to? I'd say that looks like that's approaching 2, wouldn't you say? Let's go over and do it this way, because sometimes, and I'll show you today, where it doesn't end up approaching the same value both ways. Let's see if this is the time. I'm going to type in 1.1. I get 2.21. I'm going to type 1.01, and it tells me 2.02. 1.001, and I have 2.002. What does it appear that your graph is approaching, that your function is approaching? Looks like 2. That's good news. That's what it was approaching this way. It looks like it's approaching the same value from both directions. At this point then, based on that table, I would say that my limit is equal to 2. Or up here, you can kind of write it at the end of that whole mess. You would say that that limit is equal to 2. And I do have you looking at the graph on Desmos. And here's the thing that's nice about that. You can do it on Desmos. You can also do it on your graphing calculator. Desmos is pretty slick for this limit stuff. But here's the deal. You already typed this in your y equals, didn't you? So why couldn't we just graph it? In fact, you might be looking at the graph right now. And when I look at mine, it just looks like it's a parabola that moved up 1. So I'm not sure why I have an issue with this. Why couldn't I just do direct substitution? This is a nice continuous graph. It just flows all along there. Well, here's the reason that didn't work. This really isn't a quadratic. The way that this is set up, this is a rational function. And if I look at my end behavior, this is going back to college algebra, if you have a cubic divided by a linear term, remember that you subtract these exponents. So cubed minus 1 would be an x squared. Oh, okay, so in the end, after this divides out, it kind of looks like it's an x squared or a quadratic, and that's why the graph looks like that. But there's got to be something going on right here, because x can't be 1. If you look at this, and if you're still in that value mode, you could just type 1 on your calculator as that value, and it comes back, and it just has y equals, and it's a blank, because it knows you can't let your x equal 1. It has no answer for you. What is actually happening, and you just can't see it on the graph, it does not show it, because it is plotting points super close to 1, and you can't see it, but we actually have what we call a hole in the graph. At x equals 1, so right here at x equals 1, there's actually a little hole in the graph. On Desmos, you actually can see the hole. On the graphing calculators, you can't. And on Desmos, you only see it as you slide your cursor over it, and then all of a sudden it'll pop up with a little hole there, and then it'll keep going. It doesn't have it naturally there. But it looks like then my y value is coming down towards 2, whereas up here it's coming up towards 2 to have a y value of 2. That's why my limit here was 2 as x got closer and closer to 1. Kind of tricky. You can't trust that graph always, so be careful with the graphs. The table is kind of pretty set in stone. You can usually tell what's going on the table. All right, I thought I'd do kind of a really weird function here. This one, it says the limit as x approaches 3, and this is actually what we call a piecewise function. You probably did a little bit of this in Algebra 2 and some in college algebra, but a piecewise function means you have a function, but you're only going to use a piece of it. And you might have multiple functions, and I do. I have multiple functions, and they're very basic functions. This is basically just a y equals 2. That's pretty basic. Y equals 2. That's just a horizontal line. But I am only going to be using this horizontal line, so y equals 2 looks like this. But I'm only going to use this when x is not equal to 3. Oh, okay, so I like it all right here, and I like it over here, but I do not like it right there when x is 3. I need to stick a hole in the graph right there at that spot then to say, oh, except for that spot. And then you do the second piece. And this again is a pretty simple little function. It's just going to be a y equals 0. That's a horizontal line. Except that it's only going to be plotted. Sorry, that was my dog, scared me to death. Okay, it's only going to be plotted when x is equal to 3. Well, that's hardly a line then. It's pretty much just a spot. So when x is equal to 3, that's right here. I want the y to be 0, it says. Y is equal to 0 when the x is 3. That's right here. So that hole right there where I had it must mean at that spot I'm going to really be right down here. So it's kind of a function that comes up there and it sort of approaches, but then when you get to that spot, all of a sudden you're going to jump down and you're going to plot a point down there. Kind of a weird function, wouldn't you say? Now, if you look at this graph, and remember, we're going to find the limit, right, as x approaches 3. So as I come in on the function towards 3, both directions, it would be really tempting to do direct substitution and say, well, when x is 3, my formula here says that it's supposed to be 0, because that's where that point is plotted. That's not actually going to be the case, because remember, the big word, approaches, it's all about what it's approaching. So as I come in from the left, and as I come in from the right, my y value appears to be 2. it's not really just even approaching a 2. It is 2 already at these spots. And it's approaching 2, and it's approaching 2, and it's approaching 2 and 2 from either side and either side. And then all of a sudden, at that very moment when it's 3, it pops down here. I don't care. I want to know what it's approaching as it gets really, really close to 3. And what it is approaching is 2. So the limit on this is 2. We will be working with some kind of weird functions like this, and that'll kind of help us with doing those limits so that we're forced to look at some things that aren't always very straightforward. Now, there are some times where you cannot find the limit. We have 3 situations where the limits will fail to exist. One of them is this first one. It's the limit as x approaches 0. Of the absolute value of x divided by x. Let's graph this thing. Now, I could have already had it graphed. That would have saved you some time, so you didn't have to do it. But you know what? Sometimes it's good for you to do that stuff, so you really see it and believe me. I'm going to go back to my y equals, clear out that old stuff, and I'm going to type absolute value. Remember, you find that in math, over to number, and absolute value is the first option. So the absolute value of x, close it up, divided by x, and graph that. And it does this super weird thing where, and you could put this in your notes, let's kind of sketch this in our notes. You have a line that's coming in, it's just a horizontal line at -1, and then out of the blue, it jumps up here and is at 1. Now, you can't, and that happens right here when x is 0, because look at what would happen. You can't do direct substitution. So at 0, it pops from down here to up there. Now, remember that you're looking at what it's approaching, or what the function is approaching as the x approaches 0. So as my x is approaching 0 from this way, if I had to guess, I'd say -1. Remember, it doesn't matter what it actually equals at that spot. It's what it's approaching. I'm going with -1. But if I were to come in from the other side, and think about if you were making a table, from this side you're going to be getting closer and closer to -1, and this side you're going to be getting closer and closer to +1. Well, that doesn't make any sense. If you are approaching a different value from the left than from the right, no limit exists. And that's what we write, no limit exists. Let's look at a second scenario. This is called unbounded behavior. This is actually a graph. You should know what it looks like if you remember. So let's go back to y equals and clear out that. And it's a simple one, just 1 divided by x squared. Graph that thing. And the calculators don't always show a perfect graph of it, but if you'll recall, that if it was a 1 over x, it looks like this, remember? But since it's a 1 over x squared, this pops up and they're both up top. Now, as x is approaching 0, let's look at what happens. X is getting closer and closer and closer and closer to 0. This is just going to get higher and higher and higher. Do you remember what's going on right here at this spot? It's an asymptote. So this is really never ever going to touch that axis. And same thing from this side. It's just going to get closer and closer and closer. And it would be impossible for me to pick a y value that it approaches because it goes on towards infinity. That's called unbounded behavior. F of x increases without bound. And if I can't pick out a limit, then I'm going to have to say no limit exists. And then the last one. You really do need to graph this one. It's kind of cool. Go into y equals, clear it out, and you're going to type the sign, and it opens a parenthesis, 1 divided by x. Close your parenthesis. Graph. All right, it's really tiny. We don't really see much. If I had to guess, it looks like it's like right here, and then it kind of dips down, it does something, and then it's up there, and then it looks like it's coming down. I don't know. I'm going to erase that because I'm not sure that's right, and I'm going to zoom in. And then you can see better what it does. Okay, sort of, ish. This time it looks like it's coming down, and then it's up, and then it jags and does something goofy, and it's back down, and then it's back up, and then, I don't know. Let's zoom in one more time to see what's going on there at 0. So I zoom in. And then all of a sudden I say, wait a second, it's not like crossing one time. It's like crossing back and forth a bunch of times. It's doing that thing where it's here and then it's a bunch of times. It's going back and forth. Oops, I ended up here and it's there. Okay, that's weird. Let's go one more time. See if we can get closer to that spot. And what happens is it gets crazier and crazier and crazier the deeper I get into that function. I'm going to leave that picture. I guess that's what happens. And I'm just going to go over here and say that's called oscillating between positive and negative. When it bumps up to down, and the deeper you get in, you see it more and more and more happening. All right, I'm not going to be able to pick out a y value there. There's your third example where you would write no limit exists. Those are the three scenarios. All right, that's the kind of the intro to limits. I want you to be able to find a limit by looking at a graph, by looking at a table, and sometimes if we're lucky, we'll do it algebraically also. All right, good luck on your homework.